Kulkarni. Today I'm going to explain about Module 3 from data warehousing and mining. So in this topic we have Bayesian classification. So first let us understand what actually Bayesian classifiers are. So these Bayesian classifiers are nothing but these are statistical classifiers. So they are also based upon the Bayes theorem. We'll further look into what actually Bayes theorem is. But first let us understand what actually the classification is. So these classifiers are the statistical classifiers and they have the ability or they can predict the class membership probabilities such as the probability that a given tuple is belonging to a particular class or not. So these are based on Bayes theorem and these are statistical classifiers. So these are the two key points that we need to remember. So in the Bayesian classification methods, we have two types mentioned in our syllabus, that is the Bayes theorem and naive Bayesian classification. So we'll look into them one by one. So the first one is Bayes theorem. So the Bayes theorem is named after Thomas Bayes, who was working in the probability and decision theory during the 18th century. So in order to understand what actually Bayes theorem is, we'll consider a tuple called as X. So let X be a data tuple. So in terms of Bayesian terms, this will be considered as evidence. So as usual, it will be described by the measurements made on n number of attributes. So now initially we have considered X and now we also consider another term called as H, which will be some hypothesis such that the data tuple X is belonging to a specified class C. So for classification problems, we want to determine the P of H of X, the probability that the hypothesis H is holding given the evidence or the X observed data tuple X. So according to Bayes theorem, the formula is given as PH of X equals to PXH PH divided by P of X. Now we'll understand what actually every term means. So these are having two types of probabilities. One is the posterior probability, another one is the prior probability. So PH of X is the posterior probability or posteriori probability, where H is conditioned on the X. So now, for example, we have a world of data tuples which is confined to the customers by their age and income. So we consider that X is a 35-year-old customer who is having an income of $40,000. Suppose that H is the hypothesis that our customer will buy a computer. Then we can reflect upon this example by saying that X customer will be buying the computer given that we know the customer's age and income. So now next we look into another term called as the prior probability P of H. So this is in contrast to the posterior probability. So in the prior probability, we are considering the same example that the customer will buy a computer regardless of age, income, or any other information related to that matter. So the posterior probability is based on more information than the prior probability. This is independent of the X. Similarly, posterior probability PXH is the probability of X conditioned on H. Now, considering all these terms, we can calculate the Bayes theorem by giving the formula PHX equal to PXH P of H divided by P of X. So this is all about the Bayes theorem. Now next we move on to naive Bayesian classification. So naive Bayesian classifiers will assume that the effect of an attribute value on a given class is independent of the values of other attributes. So it is assuming this assumption that it is independent on the other values of the attributes. This assumption is also called as class conditional independence. So it is made to simplify the computations involved in this, and therefore it is considered to be a naive Bayesian classification. So in order to understand in deep about how the classification is done in naive Bayesian or simple Bayesian classifier, we'll assume that D is a set of tuples and their associated class labels are present. So as usual, the tuple will be represented by the n-dimensional attribute vector, that is x equals to x1 to xn terms, depicting n measurements made on the tuple for n attributes. So next we make as another assumption that there are m classes, that is from C1, C2 up to Cm. Then given a tuple x, the classifier will be able to predict whether that x is belonging to the class having the highest posterior probability, but also conditioned on x. So this can be given by the naive Bayesian classifier will predict the tuple x belonging to the class Ci if and only if condition, that is PCIX should be greater than PCJ of x, where the j should be less than or equal to 1 and should less, and this j should again be less than or equal to m. So the maximum posterior hypothesis will be given by the following formulae. Now, after doing the second step, we move on to the third step, where the P of X is considered to be constant for all the classes, and only P of X Ci, P of Ci needs to be maximized. So we maximize this term. So if the class prior probabilities are not known, then we commonly assume that these classes are equally and likely. So next, with many attributes, the computation becomes completely expensive. So in order to reduce the computation in evaluating the P of XCI, the naive assumption that we make is that it is class conditional independence. So this is the assumption that we are making. It means that we are pre-assuming that all the attribute values that are present are conditionally independent of one another given the class label of the tuple. So this leads to the following formulae that is present in point number 4. Next, after this, we predict the class label of the X. That is the step 5, where we are predicting the class label of X. P of X is Ci, P of Ci. It is evaluated for each class, that is Ci. Now the classifier will predict that the class label of tuple X is the class Ci if and only if the following formulae. So far, we have seen about the Bayesian classification methods. Now we move on to the next part, that is rules-based classification. So in rules-based classification, we use the rules-based classifiers where the learned model will be representing a set of if-then rules in order to classify them. So we are using if-then rules for classification. So rules-based classifier are just like another type of classifiers like naive Bayesian classifiers, etc., which is making the class decision depending upon a set of rules. So these rules are nothing but the if-else rules. So these rules are good way of representing the information or like bits of knowledge. So in the rules-based classifiers, we are using a set of if-then rules for classification. So the if-then rule is an expression which is of the form if condition, then conclusion. This can also be called as a syntax of the if-then rules classifier. So it is if condition, then conclusion. So to better understand this, I'll be giving an example. So let us consider that rule is called as an R1. So if age equals to youth and student equals to yes, then by computer equal to yes. So here we need to look for the conditions and the conclusions. So here the condition is if the age is youth and the student is yes, then the conclusion part becomes he will buy a computer. So the condition that is used in the if part is called as the antecedent, and the predicted class of each rule is called as the consequent. So if the condition is getting satisfied, only then we will be able to get the conclusion. So this is all about rules based classification. So the important points that we need to remember in case of rules based classification is that the if part of the rule is called as the rule antecedent or the precondition, and the then part is called as the consequent. So antecedent and consequence are the two parts in the if then rules. So the antecedent part of the condition will consist of more than one attributes. In the previous example, we have seen that it had two attributes, that is if he is a student and also if the age is youth. So there were two conditions. So both of them are logically ANDed. and the consequent part will consist of the prediction of that class. Next, we'll move on to the next part, that is rule induction using a sequential covering algorithm. So here we've seen that the if then rules can be extracted directly from the data using a sequential covering algorithm. So this notation comes from that the rules are learned sequentially, where each rule for a given class will ideally cover many of the class's tuples. So this is the most widely used approach to mining the disjunctive sets of classification rules. So there are many sequential covering algorithms, like popular variations are there in the sequential algorithms like AQ, CN2, and more recent is the Ripper. So the general strategy behind this is that the rules are learned one at a time, and each time a rule is learned, the tuples covered by that rule are removed. And this process will repeat on all the remaining tuples. So this sequential learning of the rules is in contrast to the decision tree inductions. So because the path to each leaf in the decision tree is corresponding to a rule, we will consider the decision tree induction as the learning set of rules simultaneously, whereas here the learning is done sequentially. So following algorithm is represented for the sequential covering algorithm. So these are the set of rules for one class at a time. Ideally, when we are learning a rule for a class C, we would like the rule to cover all of the training tuples of the C and none of the tuples from other classes. So in this way, high accuracy can be achieved. So the rules will not be necessarily be of higher coverage, because more than one rule for a class, if you are considering, different rules may cover different tuples within the same class. So this is how the algorithm for sequential covering algorithm takes place. And initially the input given is D and attribute values, where D is nothing but it is a data set which consists of class labeled tuples, and the attribute values are nothing but all the possible values in the present in the set of the attributes, and the output that we are getting is set of if then rules. Thank you.